name is Ben. Today my co-speaker Sita and I will be giving a presentation titled Datalake Rock, Paper, Scissors, Iceberg with Flink, or Iceberg with Spark, where we'll focus on the topic of Apache Iceberg ingest from Kafka topics. The agenda for our presentation is as shown. We'll first provide some context and discuss a little bit about ourselves and Bloomberg. We'll then cover the motivation and why we care about ingest from Kafka to Iceberg. Then we'll cover the technologies that we're looking at today, primarily focusing on the functionality provided by both Spark and Flink as it relates to Iceberg ingest. Then we'll compare and contrast both frameworks and share some results that we collected when performance testing. And then we'll cover the features that are available to scale your ingest to multiple pipelines and tables. And lastly, we'll provide a summary to hopefully help you make an informed decision when choosing a framework. So Bloomberg's key product is the Bloomberg Terminal, and it delivers a diverse array of information, news, and analytics to help facilitate financial decision-making. Bloomberg's Terminal is a key piece of technology in the financial industry and is depended on by financial professionals ranging from banks to hedge funds. But Bloomberg is not just a finance company, it is a technology company that was founded in 1981, and there are 350,000 plus subscribers worldwide, as well as 21,000 employees worldwide, 8,000 of which are software engineers. And Bloomberg is increasingly using and contributing to open source software projects. There's a handful listed on the slide there. And Bloomberg also manages a contributor fund called FOSS that contributes capital to open source software projects that are heavily used in Bloomberg. Sita and I are part of the derivative streaming team based out of San Francisco. Our team owns various infrastructure components, but a common theme across them is they all relate to market data housed in Kafka. And our infrastructure is dependent upon by teams outside of derivatives within Bloomberg. On this plot, we're showing the scale of market data at Bloomberg. So this is across the past 12 years and showing the number of market data events or messages that were ingested per day. Back in 2008, we were peaking at around 25 billion messages per day, and that has ramped up dramatically since then. Last year, we peaked at 300 billion messages per day. And as you could probably also see from the diagram, there is a lot of spikiness in this data set. And so the systems at Bloomberg need to be performant and be capable of scaling to handle these massive loads. Here are some metrics for our data lake infrastructure. So we run an Apache Spark cluster on virtual instances. We ingest roughly 20 billion ticks per day, and that equates to roughly 350 gigabytes a day. We store our tables on on-premise S3 storage, and on the query and search side, we utilize Trino. Now let's cover the motivation for our talk today. So a typical streaming application looks something like what's shown in the diagram. You have your input data streams, in this case a Kafka topic, your streaming application, and then your output data streams. And Apache Kafka is very heavily used at Bloomberg. It's used by many different teams in many different manners. But a common characteristic of Kafka topics is that it's temporary storage, meaning that every message published to these input and output topics will be expired or purged at some point in time. It's also not easily queryable, and it's a technical interface, so it's unlikely that product or non-engineering will be interfacing with Kafka directly unless engineering builds some tool to facilitate that interaction. This makes Kafka non-ideal for workflows such as analytics, QC, and ML training, since these workflows require large data sets with large histories that are ideally indefinite. They also require an approachable interface, since non-engineering are likely to be conducting these workflows. So a lot of these workflows are made much simpler with the addition of a data lake to our system. So now if we imagine there's a separate data lake ingestion component that's consuming these topics and writing them to data lake tables, the issues related to expired or purged data are removed. Backtesting and QCing our components are now much simpler, since complex analysis can be performed using SQL queries. And this updated architecture resembles what's referred to as the Lambda architecture, where you have a layer supporting your streaming workflows and a layer supporting your batch workflows. Another benefit of data lakes is the approachable interface that is used to query your data. So with Kafka, your topic is structured as a series of messages. And on the slide, we're showing an example JSON message that can be published to one of these topics. And our data lake ingestion app will consume these messages and write them to files that are partitioned by certain columns. Since data lakes are meant for very large data, it's common to partition your data by some timestamp field to enable splitting your data into reasonably sized chunks. Now when querying this data, your table is structured with rows and columns, and the interface for querying your data is now almost always SQL. And this means that both engineering and non-engineering are enabled to do powerful analysis without engineering being a bottleneck. Now let's look at the technologies that we'll be looking at today. For those that aren't familiar with Apache Iceberg, it is a big data table format. It was designed to improve upon some earlier formats. And a unique characteristic of Iceberg is that it stores essentially all metadata in files. Other formats commonly use traditional relational databases as the metadata store, which became a bottleneck for scaling your tables to massive sizes. But when using Iceberg with a cloud object store like S3, you're capable of scaling to very large tables. So Iceberg supports tables that can be multiple petabytes in size, and Iceberg has advanced filtering features that enables pruning metadata and data files during the scan planning stage of your query. So this means that metadata or data that doesn't pertain to your query will be avoided, and this can provide 10 times performance in some cases compared to other formats. Now that we've covered what Apache Iceberg is, you may be wondering how to write Iceberg tables. And there are a handful of options. Iceberg does provide a core API that can be used to create tables, but this is primarily intended for writing implementations in frameworks and to manage your table metadata. So the much more common and recommended method is to leverage a distributed processing engine. There are a handful of implementations, some being Spark and Flink, the technologies that we're looking at today, but there are others. But currently, Spark and Flink are the most mature and common use cases. So for the majority of use cases, these are the tools to be considered. The pipeline that we're going to be analyzing today is as shown in the diagram. We have our data in Kafka that we want stored in data lake tables, namely Iceberg tables. And we'll leverage a distributed compute engine, either Spark or Flink, to facilitate that. When working with big data, an important aspect of our system is its ability to scale. And both the input and output of this pipeline utilize partitioning to handle large loads. So your Kafka topic is split into partitions that will enable our distributed compute engine to have a single reader per partition to parallelize the ingest. And our output Iceberg table is also partitioned to facilitate more efficient querying. So in this example, we're splitting our table by shape, and this will enable Iceberg to narrow its search space depending upon your query. For every Spark and Flink job that you write, there will be a DAG that represents the computation. A common DAG for a data lake pipeline is to have your source that is consuming from Kafka. In this example, a map transformation that transforms your data into the desired format, a key by or shuffle operation that will shuffle data to co-locate records belonging to the same Iceberg partition, and then a sync task that actually writes your data files to your Iceberg table. Both Spark and Flink will group together operations to minimize utilization overhead and improve the performance of your job. In Flink, this is referred to as chaining operators, and in Spark, stages are what group together operations. One key difference, though, between these two frameworks is how these DAGs are executed. In the case of Flink, all operators are executed in parallel and always running. So records forwarded from our source and map transformations downstream will be processed as soon as they arrive. In the case of Spark, your DAG is split into stages. Stages are further broken down into tasks that can run in parallel. But for a stage to start processing, all upstream stages must first be complete. And so consider this Unix analogy. Flink is similar to Unix pipes, where one command's output is redirected to another command's input. And Spark is similar to running a command that outputs to a file, and then the next command is executed after that first command using that file as input. In Flink, you control the parallelism of each operator in your job, and this will control how many instances of that operator are executed. In this diagram, we're showing a job with a parallelism of 2, meaning that there are 2 threads consuming from Kafka and 2 threads writing our data to Iceberg. In Flink, the Kafka partitions will be evenly distributed across the instances of our source operator, And so in this example, we have a topic with 6 partitions, and we are running our source operator with a parallelism of 2. So each of these instances will consume and be assigned 3 of the Kafka topic partitions. In Spark, the number of executors control the max parallelism of your job. So a stage will be broken down into n number of tasks, and each executor will continually process the incomplete tasks of the currently executing stage, 1 task at a time, until all tasks have been completed. In this diagram, we're showing an example job with 2 executors, and when consuming data from Kafka in Spark, a task will be created for each partition. So using our example topic with 6 partitions, there will be 6 tasks to consume data from your topic, each batch. Once we've completed the source and map stage, the key and sync stage will execute, and this will write our data to our Iceberg table. In this example, there are 3 buckets, so there are 3 tasks to write to our partitions. Now, you may have been wondering for both Spark and Flink why we're shuffling job or data in our job. And if we avoided the shuffle and chained the sync operation with our map transformations, we could run into the issue depicted in the above diagram. So if we have all shapes in each of these Kafka partitions, when we go to write our data to Iceberg, we'll be creating multiple files per task. In the case of Spark, we'll be creating A times B number of files, where A in this case is the number of Kafka partitions, and B is the number of updated Iceberg partitions. In Flink, the same issue can occur. So if we don't shuffle or key by our data to co-locate records belonging to the same Iceberg partition, we'll end up with A times B number of files, where A in this case is the sync parallelism of our job. And in the previous slides, we've shown how to control the number of files that are generated by our Iceberg pipeline. And we've somewhat alluded to the fact that we want to minimize the number of files that are created. To demonstrate why that is the case, we created 2 tables consisting of the exact same data, so the same number of columns and rows. But the large data files table has a single file per partition, where the small data files table has 70 files per partition. Then to test these tables' query side performance, we ran the same queries against both tables. In this example, we're just selecting the distinct security IDs from each of the tables. And in the large data files case, it took 8 seconds to process this query, whereas with the small data files table, it took a minute to process the exact same query. And this is due to the overhead of each S3 GET file request, as well as the small data files table duplicating header information in each of the Parquet files. On this slide, we're showing some example snippets of how to write to Iceberg tables in both frameworks. If you've used either framework in the past, this code will look familiar. In the case of Spark, we have a data frame that we are writing in the Iceberg format, and that format is provided by the Iceberg Spark runtime jar. In the case of Flink, we have a data stream that we are syncing to our Iceberg table, and that's provided by the Iceberg Flink connector. And as you can probably see from these code snippets, this code is very similar to other Spark and Flink code. Another important feature of our pipeline and distributed systems is fault tolerance. So when a single machine task fails, we need it to be able to recover without corrupting or losing data. For both Spark and Flink, they leverage checkpoints to durable distributed file systems to enable recovery in the event of failure. For Spark, a checkpoint is created after each batch. So a batch is processed, execution is halted, and a checkpoint is created. The size of your batch is controlled by the max offsets per trigger property when consuming data from Kafka. And so when you don't set this property, the default behavior is to consume all available messages. And when you do set this property, it'll cap the size of your batch. In the case of Flink, checkpoints are conducted slightly differently. You have this concept of checkpointing interval that you set as a user, and this will control how often your state is checkpointed. And it's also executed slightly differently. Instead of halting processing, these special messages called checkpoint barrier messages are inserted into your source data stream. And this will tell each operator to checkpoint its state and forward the checkpoint barrier message downstream to other operators before processing new records. The checkpointing interval is an important property of your pipeline because it controls your commit interval. and the commit interval will control how often data is updated in your Iceberg table. So small commit intervals will result in low latency between when data is published to Kafka and when it is queryable through your Iceberg table. Larger commit intervals will result in larger latency, but also increase the probability that the data files are appropriately sized. And so since we're covering the streaming ingest use case, we want our commit interval to be as small as possible without affecting the performance of our query side on our tables. On this slide, we're quickly touching on the feature completeness of both implementations related to Iceberg. So features are continually being added, but currently Spark does provide more support for Iceberg ingest. An area that shows is in the alter table support. So currently Spark does provide the ability to update, add, and remove columns, where Flink does not. And Spark also has a larger set of procedures for maintenance operations. So Flink does have the rewrite data files action to group together small data files into larger data files. But Spark is the only implementation that has other operations such as expiring snapshots, removing orphan files, and rolling back snapshots, as well as others. So it's likely if you utilize Flink for ingest, you'll likely need to either depend upon Spark for other maintenance operations or write some of those other operations using the Iceberg Core API. Now that we've covered the functionality and features provided by both Spark and Flink as it relates to Iceberg ingest, I'll hand things over to Sita to cover the performance results to be collected.
Hello, everyone. So far, Ben has covered the various functionalities and differences between both Spark and Flink in building Kafka to Datalake ingestion pipeline. Now, I will do a deep dive into the various components of these pipelines and compare the different approaches taken by both the systems and how they are going to impact the overall performance. But before I go into there, I have questions for the audience. Taking a wild guess, how many of you think that Flink could perform better than Spark? Anyone? That's good. And how many of you think that Spark can do better than Flink? Right, thank you. Thank you for the hands. Let's find out. As you have seen before, this is the data pipeline that I'll be looking into for the rest of the talk. And this has three main components: a read stream that reads messages from the Kafka topic, a transformer that transforms them into Iceberg table records, and a write stream that writes them as files in directional storage systems. And in order to run our performance tests, we have our Kafka topics, which are partitions and set up on on-premise Kafka clusters. Iceberg tables are set up on on-premise S3. We have Flink instances with a parallelism of 2, and Spark instances with 2 executors running. We also have a local setup on our laptop to run profilers, check the flame graphs for identifying any kind of bottlenecks in your pipeline. When we first ran our test results, we found out that Spark was ingesting around 55K messages per second, and Flink was doing so much better than Spark, almost 3 times more. And when Ben came with these test results first, I was actually a little bit disappointed, and also questioning ourselves, like, did we make the right choice of using Spark for all our ingestion and putting so much effort and resources into it? While some other teams have already moved on from Spark to Flink to do the same ingestion. And there are some other teams also reaching out to us asking, why are you using Spark? Why not Flink? And we didn't have any answers for that. That is one of the reasons we had to do this deep dive to understand and get the answers for ourselves. So we'll go to the transformer section of this pipeline first. Before comparing or evaluating any kind of technologies or frameworks, it's a good idea to optimize your business logic first. In this case, the transforming of these messages from Kafka to Iceberg records. All of our Kafka topics use either JSON or Avro encoding for messages. For this particular test and experiments, we just chose with JSON. We observed that just simply switching decoder libraries from one to other, we were able to get some significant performance improvements. We tried out with a few different decoders. We found out that Jackson JSON and Cersei were performing better than PlayJSON, and JSON ID library was performing much better than all the 3. While the decoder time was 4 microseconds in the first case, just switching these libraries, we are able to bring it down all the way to just 0.5 microseconds. And this has increased the throughput a lot, as you can see on the right diagram. Flink's performance almost doubled. Spark performance has also increased by 50%, although not as much as Flink. So we knew there were other kind of bottlenecks in the pipeline. So we now look into how Spark takes in a transformer logic. It provides multiple ways to do this, and one of them is a UDF, which is a user-defined function that takes in a data frame column, transforms them, and sends you a set of different columns. In this example, we take the Kafka messages data frame and select the value column, which is a byte array, cache it as a string, pass it to transformer, get back the intermediate columns, and finally transform them into your data frame schema columns. Spark also provides a different approach to do the same, where it provides you a map and you get a row record for every Kafka message that is read. In this approach, we just take the row as it is, transform it, convert it into like a single object that automatically gets mapped into the data frame columns. Switching from UDF to map, we were able to improve the performance of the Spark pipeline a little bit. We then looked at how Flink does the same thing for decoders. We started with a generic raw data, and when we looked at the flame graphs, we found out that this particular implementation has significant serialization and deserialization overheads when exchanging messages from a Kafka operator to the Iceberg writer operator. And this was almost taking like 60% of the overall CPU. So depending upon different use cases, Flink provides different data types. Another one of them is a raw data type. Switching from generic raw data to do the same processing, we were able to improve the performance of Flink a little bit. So with choosing the appropriate decoders and the proper Spark and Flink APIs, you will be able to like improve your transformer section of your pipeline. Next, we'll look into the read stream, which reads messages from Kafka and sends them to the transformer. In a read stream, messages are read from Kafka brokers on remote servers, and this incurs network I/O. If not properly set up, this could impact your overall performance. So Flink addresses this problem by having a separate data fetcher thread that reads these messages, parses header files, and forwards them to the transformer thread using an internal message queue. However, Spark consumes and transforms all of them in a single thread, thereby spending a lot of time just waiting for the data records to be fetched. And this was quite noticeable when you are trying to consume the same records from a Kafka broker on a remote data center compared to a server on the same data center where this was being ingested. So in order to get the same results when consuming either from a remote data center or a local data center, we simply had to change some of the Kafka configs. In this case, it is max poll records. So consumers use this configuration to fetch bulk data in batches and also repeatedly poll the Kafka broker to keep the connection alive. And the default value for this is 500. For a data pipeline ingesting at 300 messages per second rates, this could end up being 600 poll calls every second and a lot of network I/O. Simply changing this default value from 500 to 100,000 records for every poll call, we were able to significantly improve the performance of Spark, as you can see on the right side. This also improved the performance of Flink a little bit, although not as much as Spark. Next, we'll look into the impact of read patterns on the Kafka brokers. Flink and Spark set up the read stream in different ways. Flink consumes all the latest messages in real time, staying up to date without much consumer lag, whereas Spark consumes batches of messages in periodic intervals, causing this kind of a bursty read pattern. As you can see here, consumer clients, current clients like Apache Flink have more smoother read patterns because of this, whereas lagging clients like Spark have these bursty read patterns. While this impact of these patterns on the Kafka brokers could be minimal, it's good to know and keep this in mind when scaling to hundreds of applications. When forwarding messages from producers to consumers, Kafka brokers do not maintain any in-process cache. They rely heavily on something called as pace cache or disk cache. So modern operating systems use this pace cache and divert all available memory and use them for caching the pages on external storage drives. For a Kafka consumer that reads most recent messages with minimum consumer lag, it's very likely the broker forwards all the messages directly from the memory. But whereas for consumers like Apache Spark that reads delayed messages from older offsets, it's very likely that the data is fetched all the way from disk. And can this impact the overall performance? We'll find out. With some experiments, we are able to capture the page cache hit ratio on the broker by running a bunch of current clients in one test and running a bunch of lagging clients in another scenario. When we had a lot of current clients reading from most recent messages, we observed that the cache hit ratio was as close to as 100%. Whereas on the other hand, when we are having a lot of lagging clients, this ratio went all the way down to like 15%. And we found out that when we aggregated the overall consumption rates of all these clients in both scenarios, we found out the broker was able to handle 10 million messages per second at 1 Gbps rates with a really good high cache hit ratio, whereas the overall performance dropped down to 6 million messages handling at 600 Mbps in the second scenario, most likely limited by disk I/O when it reaches the I/O limits. So having current clients like Flink is beneficial for the brokers compared to lagging clients like Spark. The last aspect of the read stream is how the consumption is parallelized. Ben has already touched upon this a little bit earlier, where Flink parallelizes based on the configured parallelism. Here you can see two different task chains sharing 3 of the 6 partitions each. However, in the Spark, even though there are 2 executors running parallelly, it creates a separate task for every of these topic partitions. And as Ben mentioned before, this can cause a lot of files. It gets even more significant when you're dealing with Kafka partitions with a lot of Kafka topics with a lot of partitions, and also when writing to Iceberg tables that also have like a lot of partitions. So we will now go over the last part of the pipeline, which is the write stream. It writes these records into files stored on backend storages like S3. And we will go over some of the details in this part of the pipeline that help minimize some of the small file problem. There are different ways of writing records to Iceberg tables. One of them is a fan-out, and another one is repartition. In fan-out mode, every writer can write a separate file to each of the Iceberg table partitions, and this can cause a lot of files. In one of our production use case, we consume from a Kafka topic with 200 partitions and write to an Iceberg table of 16 partitions every 2 minutes, and this can cause 2 million files every day. And if you try to consume from this S3 bucket, it's going to be causing a lot of problems. So both Flink and Spark provide a repartition mode where you can shuffle the records before the writers actually ingest them into the Iceberg tables. So Iceberg Spark provides a repartition method where you can provide a custom partitioner that does the shuffling records for you before writing to the files. With a multi-partition Iceberg table, Iceberg documents recommend to use a repartition followed by a sort within partition operation. However, for our use case, we found out that the sort operation is very expensive, uses a lot of compute and memory, and it could also cause disk spills if not enough memory is available to it. So alternative approach that worked for us is we do repartition on one of the Iceberg table partition columns and then do a fan out for the rest. Iceberg Flink also provides a similar approach, which is called a hash distribution mode that takes care of shuffling all these records before writing to the table partitions. We discovered that Iceberg Flink takes a huge hit when hash distribution mode is enabled. And as you can see on the right side, the performance drops significantly with this. Surprisingly, Spark works just as before, even with repartition mode enabled, and writing to partition Iceberg tables. Looking at the flame graphs, we found out that the hash distribution mode uses a very inefficient partition key approach where it creates and generates a long file path string as a partition key, thereby causing a lot of expensive string operations. So we wanted to look at all the available options to see if we can fix this performance degradation, combining different row types with different partitioning schemes. Generic row data combined with hash distribution is the worst of all the combinations, where it has like a lot of serialization overheads and also using this inefficient file path-based partition key. It turns out that a row type combined with custom partitioner was offering the best of both worlds. However, Flink does not have a custom partitioner support for a row data type, so we have to go ahead and implement some custom classes for ourselves. We implemented classes like custom partitioner, custom row key selector, and all that stuff to get this working. And with custom partition in place for row data types, we are finally able to get Flink's performance to that of Spark, even with repartition enabled for partition tables. This is a very happy end results for our test cases, and we are glad to see both the frameworks performing equally well with all the optimizations in place. So with all the three components, read stream, transformer, and write stream optimized, we were able to get good performance for both the frameworks and much better than where we started. However, you will have to put some extra effort if you're using Flink to support all this extra functionality that's not there currently. And here are some performance results with various combinations for later reference. All right, so far we went through the various optimizations of all the components in a single data pipeline. In this last part of presentation, we would like to go over how to scale this to multiple applications. So Ben has earlier explained how to scale your application by increasing the parallelism, bringing up more task managers for Flink, or more executors per Spark. However, given a Spark or a Flink cluster, there is a limited number of resources that you can allocate for your applications. For example, on a Spark cluster with 100 cores, you cannot set up more than 100 streaming applications on the core, as the least configurable resource unit is just one core, and every job needs at least one core to assign to it. So how can you scale to support like multiple streaming applications that are constantly running on these kind of clusters? And also some teams have Kafka topics that have very low traffic rates compared to other topics. And when you keep on ingesting all these topics to Iceberg tables, you will not have enough resources to configure separate jobs for all of this. In these cases, both frameworks provide the ability to run multiple streaming applications in a single job. Here you can see a UI where a single Flink job is running two different streams independently and parallelly, while also sharing all the resources allocated to this job. Spark also does provide the similar approach where you can run multiple streams, although it's not like Flink where you can run all of these in parallel. Spark submits these jobs in FIFO first in, first out scheduling mode, one job after the other. And here is an example where a single Spark job with 2 executors is running 3 different streaming pipelines in periodic intervals. And this is a beautiful image where a single Spark job is running and processing all the tasks from many different streaming pipelines in a single job and scheduling them in a FIFO manner in periodic batch intervals. With some tests, we verified that Spark was actually performing well in grouping all the streaming jobs together. However, it might not be a good idea to do this approach for Flink, as for a given set of streaming applications, we found out Flink has a performance degradation, most likely because of all the threads contending for resources. And also it uses much more memory compared to Spark, as it has to keep all these messages from every stream in memory until it reads some checkpoint commit interval time. So to summarize, before evaluating or comparing any frameworks or technologies, optimize your business logic first. Use profilers and monitor flame graphs to identify bottlenecks in your pipelines, like serialization overheads. And if possible, group small tasks together to have a cost-effective setup. And optimizations are very necessary when dealing with very high traffic rate data ingestion pipelines. With that, thank every one of you for attending this session. And we hope the community has a better understanding and be more confident in choosing either of these frameworks for their next data ingestion pipeline. Thank you.